In this video, we're going to talk about improper integrals, and there are really only two things you need to think about when you're talking improper integrals. There are two things that make an integral improper. The first, and I have an example of each one here, the first one is 1 over x from negative 1 to 1. And if you think about that shape of 1 over x, in the middle of our bounds, we have an asymptote. And that's a problem. We shouldn't have an asymptote in the middle of our bounds of our integral. It doesn't have to be in the middle. It could be at an endpoint. It could be just anywhere inside the interval. But the important point is an integral is improper if there's some kind of asymptote or infinite discontinuity involved at either an endpoint or somewhere in between the bounds. The other type is probably more obvious, and that's if we have an infinite bound. We say we're trying to find the area from 1 to infinity of 1 over x. So 1 over x from 1 to infinity looks something like that. So we're saying, okay, here's 1. We're trying to find the area out to infinity. Well, that's very odd to think about. In both of these examples, we're not finding the exact area. We're finding the limit of the area, or what the area approaches as we allow ourselves to go out to infinity. So let me show you some examples. So my first example here is 1 over x squared. Now I'm going to show you the notation that's usually written here, and it really has to do again with this infinite bound. And I'm going to deal almost exclusively this in AB here with an infinite bound just for the sake of time. In BC or in Calc 2, you'll learn more about improper integrals, but for now, we're just going to deal with infinite bounds. So we rewrite our integral, and we rewrite it as a limit, because as I said, we aren't necessarily finding the exact area, we're finding the limit of the area. So we name a variable. I usually call it b, because that's what your book will call it. And we're going from an integral from 1 to b of 1 over x squared dx. Okay, so that's the first step, rewriting the integral as a limit statement. Now, I think it would be easy here to rewrite this, instead of 1 over x squared, rewrite it as x to the negative second. Okay, so the antiderivative, well, we raise the power and divide by the new power, so there it is. We're evaluating at b and 1. And I'm just going to drop this limit statement out front. So nothing is really changing from our normal working of integrals. Okay. Now, again, kind of toggling between the styles of writing this, I think it would be easier, instead of writing negative x to the negative first, I think it would be easier to write it as negative 1 over x, now that we're kind of back to this step. And of course, what we always do with integrals is we plug in the bounds, like that. And I'll still drop my limit statement down. Now, we did rewrite with that limit statement right away. It was an important step to do that, because at this point, we take advantage of that. So now you got to think, okay, as b gets larger and larger, what happens to this? Well, as b gets larger and larger, this first fraction approaches 0. Well, the other fraction has nothing to do with b. It's just 1 over 1, so like that. Well, 0 minus negative 1 is 1. And this is the limit of what our area approaches. Now, I would urge you to actually do this with fn int, and maybe find the area of 1 over x squared from 1 to 10, 1 to 100, 1 to 1,000. And what you see is that the area is 0.9, then 0.99, and then 0.999. But it doesn't matter how far you put that upper bound out, you'll never get to 1. That's the limit of the area. So again, let me be clear, we're not finding the area, we're finding the limit of what the area approaches as that bound keeps sliding out. Okay, let's do another example. So in this case, we have 1 over x, and once again, I'm going to start by rewriting with a limit statement. Now we all remember, hopefully, the antiderivative of 1 over x is natural log, evaluated at b and 1. I'm not really doing anything with that limit statement yet. Okay, that will come later. Okay, so now I plug in b, plug in 1, taking the limit as b goes to infinity. Well, okay, the natural log of 1 is 0, but the natural log of something getting larger and larger also gets larger and larger. If you think about the graph of natural log, looks like this. It just keeps growing. So this, as b gets larger, continues to grow. Well, infinity minus 0 is infinity. Here's what that means. There really is no limit. Okay? This area, if we kept, like we said in the previous example, if you kept sliding that bound out, you would just keep growing in area. There wouldn't be a limit. We then say that this area diverges, okay, because we couldn't actually get an answer. In the previous example, where we did get an answer, we would say that the area converged, and it converged to 1 because that was the area we found. But in this case, we couldn't get an actual area because infinity isn't a limit. Okay, let's do a couple more real quick examples. So in this case, we have the area from 0 to infinity of sine. And it's tempting, and a lot of times people will say, well, why wouldn't this be 0? Because, you know, sine looks like this. That positive area, negative area cancels out. Right. But remember, a limit means you have to be approaching one number. So, okay, you're approaching positive, 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 then you're approaching still positive but lessening, and then 0. And then you'll repeat. And it depends where you are in the graph to say that it's 0. So I can already tell you that this, I can look at this and say, well, it's obviously going to be divergent because it isn't approaching one number. But you'll see that the math does bear that out when we do it, okay? So we've got the antiderivative is cosine, that negative cosine, evaluate at b and 0. I plug in b, I plug in 0. And again, with our knowledge of cosine, you know, this is 1, but this limit does not exist. And you could say, yeah, but it bounces between -1 and 1. Right, it does. Cosine bounces between -1 and 1, but a limit is approaching one number. So you can't say it bounces or it depends. So this diverges. Okay. Last one. I'm going to rewrite this with a limit statement. Limit. I would urge you to get in the habit of doing that because it's notationally correct, and it also it explains at the end why you can suddenly just drop some terms out. The antiderivative of e to the negative x is negative e to the negative x. Evaluate b at 0. Plug it in. Okay. Now, of course, e to the 0 is 1, so this is -1. That works. Now, e to a negative infinity. This is like, if I can just kind of draw this over, e to a negative is like 1 over e to the b. Okay? Remember, that's what a negative exponent does. So if you think about plugging in infinity to this, you got -1 over something getting really, really large. The limit of this is 0. So 0 minus -1 is 1. So the area converges to 1. Okay? So that's our quick intro to improper integrals.